So now we need to talk about a new type of integration, and this is called line integrals. There's two different types of line integrals we're going to discuss. The first one is often called scalar line integrals, okay? And the next one would be vector line integrals. And we'll spend more time on vector line integrals, but we start with scalar line integrals. Now, these are pretty simple in concept in that they're very similar to your single integrals you learned way back in Calc 1, where you integrated a function over an interval. In this case, what we're going to do is we're going to integrate a function over a curve. Okay? And that's really the big thing here. We're going to integrate a function over a curve. Now, what type of function we integrate over a curve is really the difference between a scalar line integral and a vector line integral. So if we're going to integrate a real valued function over a curve, this is what a scalar line integral is. If we integrate a vector field, which is just a different type of function in a sense, over a curve, that's what we're going to call a vector line integral. All right, but let's start with scalar line integral. So the idea is fairly similar to what we would do in Calc 1. So in Calc 1, we would take an interval that we were integrating over. So we have, say, some interval that we're integrating over on the x-axis from a to b, and we would subdivide that up. Each one of those subdivisions, the width of that we call delta x, and then we use that to create the heights of the rectangles. Okay, we use that for the width, and then we would create the height of the rectangle based off of the function. We're going to do this similarly. Integrating over a curve, let's say this is the curve we're going to integrate over. So it's not this straight interval, it's curved. We will subdivide it, okay, into these separate sub-intervals, and these sub-intervals all have a distance to them. Now, it's not the straight distance here, it's a curved distance, so it's an arc length, but they do have a distance, so we can call that the width here. And we subdivide it more and more and more and more and more. We would create more intervals, therefore we create more rectangles, etc. And so once we do that, that will be then the width of each rectangle. The height of the rectangle will go up to the function value. Now, when we do this in Calc 1, we could either put the left-hand side of the rectangles where we hit the function, we could do the right-hand side of the rectangles where we hit the function, we could do the middle of the rectangles where we hit the function. It's really just a matter of where do we get the height along this interval. And we saw in Calc 1 that it really doesn't matter whether you use the left hand, right hand, middle, because if we subdivide this more and more and more and more and more, the idea is that this width becomes so thin that the left hand side, the right hand side, or the middle all become virtually the same thing. So we're going to pick some sample point inside the interval. So here's your first interval. We'll pick some sample point in the interval. Again, that could be the left hand, right hand, middle, anything. And that's where we're going to get the function value. So we're going to go there. From that point, we're going to go up and get the height of the rectangle by plugging it into the function value. So we have the width, which is the length of the arc. Okay. We have the height of the rectangle based off of the function value. And we're going to add all those rectangles up, which is going to give us an area. It's just going to be a curved area instead of a straight flat area. All right, so once we add all those up, that should give us our estimate. Once we get our estimate, what we should then do is take the limit as the widths go to 0, so the number of rectangles goes to infinity, or this distance here goes to 0. And what that's going to do is that's going to create an integral. Okay, and this is what we call a scalar line integral. Okay. Now, how we're actually going to compute that is basically using this formula here. So let's say we have a curve, R of t is a parameterized curve. Okay, we talked about these vector valued functions. Okay, vector valued functions trace out curves in 2D and 3D space. So we're going to parameterize a curve through one of these vector valued functions. We're going to let t range from a to b along that curve. And if we have this multivariable function, f of x, y, z, and the derivative of r are both continuous, then if we wanted to integrate this function over this curve, Okay, we integrate this function over the curve specifically with respect to the arc length, these distances here. This is how we're going to get it done. We're going to basically be able to get this done, do this computation, by converting this to a standard single integral that you would have done back in Calc 1. How? We basically have to parameterize everything. So we parameterize the arc length, and we calculate it using the magnitude of r prime. We saw that back in the beginning of the semester. We have to parameterize the function over the curve by taking the curve and plugging it into the function. So finding f of r of t, we'll talk about how we do that. And then the interval is the interval of t's that we're working with along the curve. So if this is where t is a on the curve, and this is t of b on the curve, that's the interval we're going to talk about. So this is the formula for how we're going to get this done. So this picture further illustrates the difference between the single integral in Calc 1 where you integrated over an interval. Okay, here's your interval, and this is your single integral. And this is now the scalar line integral. So we have this curve here that we're integrating over. That's sitting in the xy plane. Okay, we subdivide that curve. Then we have this function that's here in the xyz space. And we're going to find the area in between. So we're still basically talking about finding the area in between, but now it's a curved area instead of a flat area. So picture taking this and taking this x-axis and twisting it like this. And then you would see the sort of, this was a piece of paper here. You would see this piece of paper bending, but it would still be flat, two-dimensional, and you would find the area in between. This figure here further illustrates the same concept. This red is a surface sitting in 3D space, so this is some function of x and y, or even x, y, and z, if we were talking about even more variables. So we have the surface, we have this curve that is sitting in the xy plane down here. Okay, let me use a different color. So we have this curve down here, and we want to say where this surface sits over top of the curve, we're going to find the area in between, and we're doing it through a series of rectangles, and the more rectangles we put in, the better this area is going to be. But the way we calculate it is very similar to what we did in Calc 1. Okay, subdivide this curve up, that'll be the width of each one of these rectangles, take some point inside that curve, that's the place where you're going to get the height of the rectangle. So once you have height and width, you add them all up, let the number of rectangles go to infinity, you get the area. So if we were going to integrate this function here over the curve, okay, we were going to compute this scalar line integral, we would need the curve. This should have an r in front of it, r of t. So our curve is already parameterized as a vector valued function. This is the surface itself that we're integrating over that curve. And this is the interval of t's that we're going to work with on the curve. So we have a starting point and an ending point. So this is basically pulling together a lot of different things we've talked about over the course of the semester. Vector valued functions, multivariable functions, and integrating these over the curve with respect to arc length. So the way we're going to do it is by integrating from a to b of f of r of t times the magnitude of r prime of t, dt. And so we got to calculate all this stuff. First thing we're going to do is we're going to calculate f of r of t. Now how do we do that? How do we take this and plug it into here? Okay. Well, the way we take this vector function and we plug it into this real function is essentially saying, well, this first component will be x, the second component will be y, and this third component will be z. So I'll plug this in for x, this in for y, and since there are no z's, this isn't going to get plugged in anywhere. So f of r of t, if this is f, would be the square root of 4 cosine t squared plus 4 sine t squared. in which we're going to get the square root of 16 cosine squared t plus 16 sine squared t. Pull out the 16, you get square root of 16 times cosine squared plus sine squared is 1, so you're going to get 4. So f of r of t is 4. We know that that's not going to always be a constant there. I'm sure you can see that sometimes it'll be some function of t, but nonetheless that's f of r of t for this example. Then we need to find the magnitude of r prime. So first we need to find r prime, which we should easily be able to do. We've done derivatives of vector value functions before. So for minus 4 sine t, 4 cosine t, and 3. And the magnitude of r prime will be the square root of 16 sine squared t plus 16 cosine squared t plus 9. Pull out 16 out of here. Sine squared plus cosine squared is 1, so we get square root of 16 plus 9, and that would be the square root of 25, so 5. We also know that the magnitude of r prime isn't always a constant, something we've discussed multiple times already. So these are both constants, but oftentimes you're going to be left with a function of t, and that's what you're going to integrate. The a to b is the interval of t's we're working with here, so negative 2 pi to positive 2 pi. We're going to do f of r of t, which is 4, times the magnitude of r prime, which is 5, and integrate that with respect to t. So this would give us 20t from negative 2 pi to positive 2 pi. We plug those in, we get 20 times 2 pi minus 20 times minus 2 pi. So we get 40 pi plus 40 pi gives me 80 pi. Once you get to this point, it's a single integral. That's the easy part. It's a single integral with a single variable. I mean, we've done double integrals, triple integrals with multiple variables. And so when we can go back to just doing a single integral with a single variable, the variable is now t because we parametrized everything. And that's really the key here. The reason why we do all this is because we're going to basically parametrize everything in terms of t, so we can do a single variable and therefore a single integral. But once we get to that point, easy stuff. It's just a matter of converting this integral of this function over the curve to this single integral using that formula. So here's another example. Here's the function that we're integrating with respect to arc length over the curve. Here's the curve itself with the interval of t being from 0 to 1. So we're going to integrate this multivariable function over this parametrized curve. It's already parametrized with this vector value function with these t values. So we're going to need to do the integral from a to b of f of r of t times the magnitude of r prime of t dt. So f of r of t, again, first component x, second component y, third component z. That's how we're going to plug it in here. So we're going to get x times y, so that'll be 2t times 2, plus y, which is t, plus z, which is 2 minus 2t. If we simplify that, this will be, what, 2t squared. This will be t, and a minus 2t will be minus t plus 2. So that's f of r of t. Then we need r prime, which is just going to be 2, 1, negative 2. And we need the magnitude of r prime. Should be the square root of 4 plus 1. 4 plus 1 plus 4. So that's going to be 3. So then the integral that we want to do from 0 to 1, because that's the interval of t we're working with, will be 2t squared minus 2 plus 2, minus t plus 2, times 3 dt. Again, single integral at this point. With respect to t, this should be easy. 3 is a constant multiple, so I get 3 times, 2t cubed over 3 minus t squared over 2 plus 2t. Between 0 and 1, it's going to give me 3 times, 2/3 minus a half plus 2. If I plug 0 in, I'll get 0, 0, 0. So this is it. So once I do 2/3 minus a half plus 2, I'm done. So I convert to 6. I have all this space up here. I'll do it up here. So I have 3 times, 4/6 minus 3/6 plus 12/6. So 3 times, what's that, 1/6, 13/6. So 39/6, so we'll simplify that. 13 halves. 13 halves. Okay? So there's your integral. So you see, scalar line integrals, integrating a function over curve, is only going to be as difficult as the integral that you come up with is. But the integral you come up with after you apply this is a single integral with a single variable. So by the time we've gotten all the way through this Calc 3, this should be easy. No matter how, complicated this integral is, you should be able to handle it. So now we move on to vector line integrals. We're going to spend a lot more time on this. So when it comes to vector line integrals, we want to integrate a vector field over a curve. This is a little bit more involved in that there's a bunch of different ways that we can get this done. And there's definitely some reasons for doing this as well. Now, the most common reason for calculating a vector line integral is so that you can calculate the work done by force, which you should be somewhat familiar with just from physics class. So, if we wanted to calculate the work done by force, an example would be something like the example I give you here, where we're talking about backpacking up a mountain, and you're working against the Earth's gravitational field. So when you walk up a mountain, so we have a mountain here, right? You have the Earth's gravitational field pulling down on you, okay? So as you traverse the mountain, whether you go straight up the mountain or whether you zigzag yourself back and forth, the path that you're traveling on is the curve that is going through the vector field, being the gravitational field, okay? Another example is you have a stream, you have a fish swimming in that stream, okay? The current is traveling this way. The current in the stream is the vector field. The path that the fish is traveling on is the curve that is passing through that vector field. So we're integrating this vector field over this curve. We're integrating this vector field over, say, this curve. And what we're going to compute is the work done by force of you backpacking up the mountain or the fish traveling through the water. You don't always have to be going against the gravitational field either. We could be coming down the mountain. We could be going with the current. But either, no matter what, it's the curve that you're traveling on passing through a vector field. Okay. So the first way you do it is most similar to the way we did the scalar line integrals. So if we want to calculate this integral of this vector field over the curve with respect to arc length, okay, we would need to parametrize everything. So we have a vector field, and that vector field could be a three-dimensional vector field, two-dimensional vector field. It really just depends on what vector field we're working with. And we have a curve that's passing through that vector field. We need the curve to be parameterized, so the best way to do that oftentimes is with a vector valued function. And we want an interval of t that we're working with along that curve. The curve should be a smooth curve, and we've talked about smooth curve before when we first started talking about vector valued function curves. And it just has to do with continuity. And so if we have all this, what we're going to need to do is we're going to need to parameterize the vector field with respect to arc length, but also we want to turn this into a single variable function in the end that we're integrating, right? Because we're doing a single integral. And if we're doing a single integral, we need a single variable function for us to do that. This vector field is not that, right? This vector field is comprised of multiple functions inside the composition of a vector. So what we want to do is if we apply this formula, it allows us to essentially convert this to a function of t. So we do f of r of t, very similar to the scalar line integrals. In this case, f is a vector field, though. We want to plug r of t into that. How do we do that? Basically, we do it the same way we did before. Then instead of doing the magnitude of r prime, we're just going to do r prime here. And this is still going to be a vector. This is still going to be a vector. But if we do the dot product between them, this whole thing is now no longer a vector. Because remember, the dot product between two vectors is no longer a vector. But what is it? It's whatever the vectors are made up of. Well, this thing would be made up of a bunch of functions of t. This, in the end, when we plug r of t into f, would be a bunch of functions of t as the components of that vector. So the dot product between them becomes a function of t, and that's how we're going to do this. Another notation that you'll see for vector line integrals is this notation. It doesn't really get to the heart of necessarily how we're going to do this so much, but it is another notation. So the big difference between scalar line integrals and vector line integrals is what are you integrating over? Curves in both cases. So that's the difference from standard integrals from before. But the big difference is whether you're integrating a function, a real value function over a curve, or a vector field over that curve. Okay? And the step up from what we've done before is that we're integrating over curves. Right? We never integrated over curves before until we started talking about these line integrals. So here we want to find the vector line integral for the function along the path. So here's essentially the vector field we want to work with. This is the curve we want to integrate that vector field over these particular t values. So if we're going to integrate this vector field over the curve with respect to arc length, we should do it by integrating from a to b of f of r of t dot r prime of t dt. So first we need to find f of r of t. Now how we're going to do that is very similar to how we did it with functions. We'll call this x, we'll call this y, we'll call this z, and we're going to plug them in accordingly. So this will go in for x, this will go in for y, this will go in for z, wherever we see an x, y, and z. In this case, since x, y, and z are the three components, we just get cosine t, sine t, and t. Then we need r prime of t, which again, that should be really easy to find. So we're going to get minus sine t, cosine t, and 1. And then we need f of r of t dot r prime of t. So the dot product between these two is easy. This times this, plus this times this, plus this times this. So we're going to get minus sine t cosine t plus sine t cosine t plus t. You see these two will cancel, so we just end up with t. So that's the function we're going to integrate with respect to t. That's what this ends up being. The interval of t is 0 to 3 pi. T is the function with respect to t we're going to integrate. And so we're going to get t squared over 2 from 0 to 3 pi. So we get 9 pi squared over 2 minus 0. So 9 pi squared over 2. Seems simple enough, but it depends on the vector field and the curve. So what we're going to see over time is that this method of integrating a vector field over a curve, is not very effective for some examples in that it creates a fairly difficult integral. Sometimes the curve itself that you're trying to integrate over is not very easy to parameterize. Sometimes the vector field itself is fairly complicated. And then trying to compute this piece that we're going to need to integrate can be quite cumbersome. And so we're going to come up with other ways of doing this in the long run. But right now, this is how we start calculating the work done by force, or calculating what we call a vector line integral. So here's another one. Find the work done by force from 0, 0, 0 to 1, 1, 1 on the curve, where the vector field F is given by this vector field. Now notice there's something different here, in that it didn't give you the A and the B. It didn't give you the interval for t that we're working with. Okay? What it did is it told you what point on the curve we would start at. That point is on this curve. And what point we're going to end, okay, again, on this curve. So we have the curve, and the curve is parameterized with this vector value function. We just don't know what the interval of t is. Well, it's pretty simple in that if we look at r of t being t squared, t to the fourth, we would have to figure out what, remember, these vector value functions, sorry, I should say something first. These vector value functions, remember, are a series of vectors, all starting at the origin, that point to points that then trace out a curve, right? That's how these vector value functions work. And since they start at the origin, the point that they point to, say A, B, C, is the same as the components of the vector that got you to that point. So what I need to do is I need to figure out what t value did I plug in that got me 0, 0, 0 as my vector, which then pointed to the point 0, 0, 0. So the t value I plugged in has to make this 0, and this 0. Well, the only t value for that's going to happen is 0. So the first value of t that we started with would be 0, and then we do the same thing all over again. What value of t would create the vector 1, 1, 1, that would then point to the point 1, 1, 1. And so what t value would I use? In that case, you could see very simply, it would have to be a t value of 1. T value of 1 here, here, and here would create 1, 1, 1. So then that ending point would be 1. So we can create the interval of t fairly simply by knowing the points that we start and end with. So that's the first part. Second piece is to calculate the vector line integral. And so in order to calculate the vector line integral, integrate this function with respect to arc length over the curve, we have to do the integral from a to b of f of r of t dot r prime of t dt. And so f of r of t is going to be, remember, x, y, z. And so we're going to get 3t squared minus 3t, 3t to the fourth, and 1. R prime is going to be 1, 2t, and 4t cubed. And so then if we do f of r of t dot r prime of t, we just have to do the dot product between these two vectors. So this times this, plus this times this, plus this times this. And so that's going to give us 3t squared minus 3t plus 6t to the fifth plus 4t cubed. So that's the function we're going to integrate. The interval is 0 to 1. So then the vector line integral would be 0 to 1 of, let's write this, 6t to the 5th plus 4t cubed plus 3t squared minus 3t dt. And so that's going to give me t to the 6th plus t to the 4th plus t cubed minus 3t squared over 2 from 0 to 1. So 1 plus 1 plus 1 minus 3 halves. So 3 minus 3 halves would give you 3 halves. And so the vector line integral, or work done by force, where this curve here is traveling through this vector field from this point to this point, is calculated at 3 halves. So, pretty easy to do again, but this is going to start to become harder and harder. And so we're going to move away from this formula and onto other types of methods for integrating vector fields over curves based off of maybe what type of curve we have or what type of vector field we have. But note that this formula for integrating a vector field over a curve for doing this work done by force is not dependent on the vector field. We didn't say the vector field had to be any specific type of vector field. Any vector field will work here. It doesn't depend on the curve, really, being a specific type of curve, having any type of properties to it. Any curve, as long as it's parametrized, okay, will work here, and we can use this formula to calculate the work done by force. It's just the practicality of using that formula comes in question when it comes to certain examples, and we need to develop more ways of computing this vector line integral.